Now we can formally find or define independence. So we know that events A and B are independent whenever the probability of B given A equals the probability of B given the complement of A, which is equal to the probability of B. That's because if you know that the probability of B given A and the probability of B are the same, or the probability of B given not A and the probability of B are the same, essentially what's happening is knowing A has no relevance on the probability of B. We can see that the original multiplication formula is just replacing this probability of B given A with probability of B, which is true when A and B are independent. So let's use the examples that we've already done. Being male and surviving on the Titanic. Are they independent? Well, let's take a look at the probability of being a male and the probability of being a male given survival status. So the probability of being a male is 1731 out of 2201. That was a very high probability on the Titanic being a male. Probability of being a male and surviving. Well, that's 367 out of 711. I'm sorry, probability of being a male given survival. So that means 367 out of 711. These are clearly not the same. The probability of being a male was way higher than the probability of being a male given that you survived. So these are not independent, otherwise known as dependent. So not independent. Are they disjoint? They are not disjoint either, because it is possible to have been a male and survived. So notice that anytime this probability is greater than 0, you do not have disjoint events. Because if you're given one thing and they're disjoint, then the other thing has to be 0. We're being a senior and driving status independent at Wabansie Valley. Sorry about that. So we look at this and we have the probability of being a senior and the probability of being a senior given that you have a legal driving license, driver's license. Probability of being a senior, if we remember, was 0.23. The probability of being a senior given that you have a driver's license was 0.16 divided by 0.33, 16/33. And that is, these two are definitely not the same. So once again, not independent. Are they disjoint? Once again, not disjoint. If we have a random sample, then we have to take into account the fact that these two will just be really close to each other, because if you have a random sample, it's probably just collecting data and you don't have all of the information. You have enough to make a pretty good guess. But if you want to know how close those two have to be, you have to take AP statistics, because that's beyond this course. When airline passengers go through security checkpoint, some are subject to additional searches. So let's take a look at this information. So we'll say laptop, not laptop, and we will say searched and not searched. So let's fill the table out. So we know that 30 of the 145 passengers with a laptop, so we had 145 passengers, 30 of them were searched, which means we had 115 not searched. There were 203 without a laptop, and 42 of them were searched. So if we do a little bit of subtraction, we end up with 161. 72 there, 276 there, 348 total. That's our two-way table. What's the probability that we have a randomly selected passenger and that person was searched? So if we take a look at a randomly selected passenger, that's 72 out of 348. We could reduce that fraction, but in the interest of time, I won't. What's the probability that that person that was randomly selected didn't have a laptop and was searched? So this is an and probability. So the probability of no laptop and searched. So we have 348 people. And if we look at not having a laptop and being searched, there were 42 of those. What is the probability that they had a laptop or they were searched? So that's probability of laptop or searched. So that's probability of laptop plus probability of searched minus probability of both. Or once again, we can just look at individual elements of the table that make sense. So the probability of having a laptop was 145. Probability of being searched was 72, but we only need to look at the non-laptop searches. So that's 145 plus 42, which is 187 out of the total 348 people. What is the probability that a person without a laptop? So we're given that they don't have a laptop. And we want to know that they were searched. So the probability of being searched given that they don't have a laptop. So that's 203 in our denominator. And then searched is 42. What's the probability that a person who was searched didn't have a laptop? So this is the probability of not having a laptop given that they were searched. So that means our denominator is 72, since we're only looking at the searched row and not being searched. I'm sorry, not having a laptop is 42. We need to figure out if the events laptop and searched are independent. They're clearly not disjoint because we have non-zero probabilities here and here. Because if they were disjoint, non-zero probabilities for not the ones that I circled, but if we have probability of searched given laptop, there clearly are things there. So if we have a laptop and being searched, we can't possibly have disjoint events. And like we said, probability of being searched and have a laptop, there were elements in that case. There were 30 in there actually. So that means that they're not disjoint events. Okay, probability that L has a laptop and S was searched are independent. So let's take a look at the probability of having a laptop. And we want to figure out if the probability of having a laptop, given that you're searched, is the same. So the probability of having a laptop was 145 out of 348. Probability of having a laptop given they were searched. So if we look at the chart, given they were searched is 72, having a laptop is 30. So in that case, so the probability of searched and laptop is 30. So if we take a look at this, we have to kind of figure out what's going on. So we have 145 divided by 348. That gives us about 0.416 repeating. 30 out of 72. Oh my goodness. It's the same. Since they're the same, that means they are independent. So that means that TSA was not flagging people that had laptops on this particular day. Suppose in a certain company, 5% of employees use illicit drugs. The company decides to test all its employees for illicit drugs with a test that has a false positive rate of 3% and a false negative rate of 10%. Those are defined in this note. Let D be the event that the employee uses drugs, and P be the event that the person tests positive. So let's express the information in terms of P and D. So the probability of being on drugs in this company is 0.05. We also know two other pieces of information about the test. So the probability of a positive test given that you do not use drugs is 0.03, and the probability of a negative test or not positive test given you use drugs is 0.10 or 0.1. So now we're going to make what's called a tree diagram. A tree diagram gives us lots of different probabilities, and it kind of branches out. So the probability that someone uses drugs is 0.05. Probability that they don't use drugs is 0.95. Now our diagram continues. So the probability that someone gets a positive test, given that they use drugs, is going to be 0.97. Probability that they, no, wait a minute, that's not true at all. Because the thing that I actually know is the probability that I get a not positive test given that they use drugs. That's 0.1. So that means the probability of a positive test given that they use drugs is 0.9. Because these two things have to add up to 1. Now, if I take a look at the probability that someone doesn't use drugs, it's 0.95. Probability that they get a positive test would be the false positive rate of 0.03, which means 97% of people who don't use drugs get a non-positive test. So now what I can do is I can figure out all of these probabilities by multiplying straight across the tree. So 0.05 times 0.9 gives me 0.045. That's equal to the probability that somebody does drugs and has a positive test. Once again, notice that these two numbers will add together to be 0.95. If I add all of these together, I get 1, which makes sense because that's 100% of the cases. What is the probability that a person uses drugs and tests positive? So we already calculated that. Person uses drugs and tests positive is the first row on our little tree. That's 0.045 or 4.5% of all of our cases that we have. What's the probability that a person tests positive? So the probability of a positive test is going to be just adding together the two cases where I have positive tests. So that would be 0.45, or I'm sorry, 0.045, because this is a positive test. And then I have one other positive test. So that's 0.0285. So if I add those two together, 0.045 plus 0.0285, I get 0.0735. So the probability that a person tests positive is actually greater than the probability of having a drug user in this company. What's the probability that a person uses drugs or tests positive? So the probability of drugs or positive. So that means that I have the probability of using drugs plus the probability of testing positive minus the probability of both. And if I look at this case, probability of using drugs was 0.05. Probability of testing positive, I just found, was 0.0735. And then the probability of drugs and positive test, well, if I look at the probability of drugs and a positive test, that was 0.045, right? So now what I do is I just add these together. So 0.05 plus 0.0735 minus 0.045 gives me 0.0785. If a person tests positive, what is the probability that they use drugs? So probability of a positive, or I'm sorry, what is the probability of using drugs given that you have a positive test? So probability of a positive test, we found out, is 0.0735. The probability of using drugs and having a, or using drugs and having a positive test, and is an upside down. We found that was 0.045. So if I look at this, 0.045 divided by 0.0735 gives me approximately, so I'm going to change this, 0.6122. So if a person tests positive, we're only 61% of the people that test positive are actually using drugs in this case. That's kind of crazy. When we look at the false positive and false negative rates, that's actually not too bad. I mean, you wouldn't think, but what ends up happening is we're getting 3% of non drug users tested positive, and a high majority of the company did not use drugs. Um, and there's actually a reason why that would happen in a case like this, and we'll talk about that a little bit more. Which of these errors is worse for the employees? Well, I would say if you have a false positive, that would be pretty bad because you are being asserted that you use drugs even though you don't. Um, for the company, it could go either way. You could get lawsuits with false positives or fire good employees. But at the same time, a false negative would be bad because you may have somebody that's really losing productivity for you that ends up sticking around due to the false negative. How can we change the probabilities? We'll talk about that in class.